Start record. Yes. Okay. So you see me. Nice. Okay. So any questions about Great Wall? You know the project firsthand, right? Because you have worked on it. Any question?
Okay.
Any comments? Any ideas? You can also talk about your ongoing project. Yes. Go ahead.
Okay. Perfect. Okay, I guess. Yeah. So, Great Wall, as I know of it, it's more of a list of tools, right? That has many use cases. So, I think the question I will ask is, okay, say we have Great Wall and we have the what's the name of this? We have the Great Wall, and then we have the other stuff we are working on, like Mooncake and TLP. So, how does these things tie together with the Great Wall Protocol?
Very good. So Mooncake is an interface to prevent side channel attack. A side channel attack is a broader concept. It refers to ascertaining information about associated information. So for instance, we have energy, you have memory consumption, energy consumption, time for a certain process. We have the acoustic emanation of typing. If you type something, right, it makes noise. This noise can be captured and then processed to try to ascertain what is being typed. Also, you have the so-called shoulder surfing. Somebody might be looking to see what you see your hands typing, but also look to your screen and somehow filming, and you're capturing, externally capturing your screen. Maybe there is a keylogger, things like that. But again, if it is indirect, we call it like the acoustic emanations, like trying to ascertain the heat signature in the keys because your fingers touched it and then heated it. Anything that is indirect is called side channel attack. Right? If you monitor the consumption of energy and then you make inferences about what is going on that consumes this amount of memory over time, this is a side channel attack too. If you monitor the consumption of memory over time and then you say, this much memory has been allocated and then dropped and then allocated again and then dropped, and then if you monitor that over time and use that to make inferences about what is being calculated, this too is a side channel attack, etc. But then again, in our case, we are focusing on what? Passwords. Passwords, of course, the process of typing passwords is a huge window of vulnerability, right? It's a huge surface of vulnerability because, again, you have the fact that it's a critical piece of information that somehow is being typed. The process of typing, of course, creates the so-called acoustic emanations. There is the sound of the typing. Also, possibly, somebody may see your fingers typing and record that somehow, which of course is catastrophic. And of course, could be that even if temporarily, each digit of the typing of the password appears, even if it's immediately substituted by an asterisk, if it is the fact that the given interface shows the each digit temporarily at each point to then change it to an asterisk, in this moment in which it's shown, it can be recorded and then it is game over, right? Because if an attacker does that recording, and then they learn the password. So Mooncake, as you know, as an interface to mitigate that, to diminish the surface of attack, right? You have worked on it. Can you describe what you know about it?
Well, okay. So Mooncake, like you said, it's an interface that tries to build a solution around acoustic elimination, or more like a side channel attack. And Currently, we decide to use hardware, like the hardware button on the user's device, that is for mobile, where you have certain key presses and the duration of those key presses. Those could mean different key inputs. So with this, it would be harder to do a site attack, for example, guess or use acoustic emulation. Then on the keyboard, of course, the natural finger, when you're resting on the keyboard, you have your fingers on the ASDF G key, that is the middle keys. Using this now, you could, for in fact, create a map of those characters, right, that you're trying to impute. For example, ASDF might translate to something in the table that you have in memory or something like that. But then again, there is one thing I always wanted to ask about this. It's the user experience. It seems a little bit technical, if you know what I mean. Why I say a little bit technical is some people who are not really too familiar with technology might find it a little bit confusing to use, especially the keyboard, like desktop version.
Okay, let us see that in action, shall we? Okay, so you see the screen, correct?
I see the screen.
Let me see if it is being captured properly. Yes, it is. So let me just do something here. Stop present. No, ignore. Okay, ignore. Okay, now it's better now. Well, so what do we see here? This is Formosa. This is Formosa type global. Of course, Formosa is an expansion of BIP39. Just like or said it backwards, BIP39 is a particular case of Formosa. Of course, BIP39 came first, so it's more logic to frame Formosa as an expansion because it came later, of course. But anyway, here you have it, right? So how does that work? Here you have the mnemonics and the condensation of the mnemonics. So just like BIP39, let us see that happening. We can copy that. Let us see that happening. Go here to converter for those watching that don't not yet know it. There is a chance that the program just will crash. Okay, so if that happens, please forgive us. But let us try to see that happening anyways. So we are going to try to convert global into BIP39. Here you have it. Multiple. Okay, so something went wrong. Let us try. Yeah, at least it didn't crash, right? It flagged an error. Let us try to recreate the one again. Okay, so clear here. Let us run it. Multiple of 6. It should be like that. Yeah, multiple of 6. Maybe okay. An error went when maybe accidentally cut one word. Okay, let us try again. Okay, convert. Yeah, okay, convert. Let us try to see. Finally. Okay, so how many words do we have it? Let us count. This is the condensation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Correct. So this is a valid BIP39 seed. Let us then change. Okay, now we will have to do the inverse. The inverse. Hopefully it won't crash. Please forgive me if it does. Okay, so finally. So we went convert Formosa to BIP39 and then backwards. And people in the recording will be able to see it really came back to the same, right? Let us redo that, by the way. We could, of course, do as many times as we want. So let us see if we then convert back again, it will be the same, right? The recording will show, okay. So again, global, yes, and then here BP39, okay, and then convert. Okay, peel, beginning, and then ending with a string. So yeah, I just assume it's all the same. Okay, so what is happening here? Each such word here in BP39 has how many bits of entropy? Ibrahim?
Yeah, sorry?
How many bits of entropy each word conveys? Each BP39 word conveys. How many?
That should be 39, right? That should be 39, right?
Here, no, how many bits of entropy each word conveys?
16.
Wrong, it's 11 because each word is randomly selected from a set of 2048 possibilities. So 2048 is 2 to the 11. So what BAP39 does is it lists, it has that fixed list, and then the trivial thing to do, and which is done in fact, is each word is mapped into a number, the indexation, the position of the word in the list. -1, of course, but this is rather trivial. And then the binary indexation is just the binary version of the number of the word in the list. Simple as that, right? Now, something slightly more complex happens here in the in Formosa, because now you have different lists for different words. The first word is always a nationality, particularly in this theme, right? The second is always a profession. The third is again another nationality from the same list as the first. And then again you have a profession. And then you have a number between, I think, between 0 and 63. More about that later. And then you have a place. And then repeat. Again, first a nationality, then a profession, then a nationality again, and a profession again, and then a number again between 0 and 63, and then a place again. And then you have that 4 times over. Everybody follow me? Okay?
Yeah. So, quick question.
Yeah,
so the number from 0 to 63, that is randomly decided, right?
Everything is random, and everything is uniformly random, meaning all the options in all the lists have the same probability. It's a uniform decision, uniform probability. Why is this important? And what is the sense of that? All the list of nationalities have a power of 2 number of options. If I'm not mistaken, 64. And then you have 32 options for professions. And then the same 64 options for nationality, and then the same 32 options for profession. And then you have 64 options for number because it's between 0 and 63, right? And then you have 32 options for place. Why is that interesting? Because then, again, this is just like on BAP39, you have a power of 2 number of options, which is 2048. Here we have all round numbers viewed from the power of 2 point of view. Does that make sense? So each new element you have adds a quantity, an integer number, a whole number of bits. And then guess what? You have 64, and then 32, and then 64 again, and then 32 again, and then 64 again, and then 32 again. What is the result? 6. 64 is 2 to the what? What is power? What is log base 2 of 64? 64 is equals 2 to the 6th, and then 32 is 2 to what?
Are you asking question?
Yes, I am asking. Yes, 32 is what power of 2?
32?
Yes.
Power of 2?
Yes.
64.
No. 32 is equals 2 raised to what power? 32 is 2 to 5, and 64 is 2 to 6. So how many bits do you have? In the first word is 6, and then in the second is 5, and then in the third is 6 again, and then in the fourth is 5 again, and then in the fifth is 6 again, and then in the last one, the sixth one, is 5 again. So in total you have 6 plus 5 plus 6 plus 5 plus 6 plus 5. That gives you 33. This is not a coincidence, because 33 equals exactly, it is the exact equivalent to 3 BAP39 words, because what? Each word conveys you 11 bits. Times 3 gives you 33. So this is not a coincidence. It means that each Formosa sentence gives you exact as much cryptographic strength as what? 3 BIP39 words. So in one hand you have 4 sentences, and on the other hand you have 12 words, and this matches perfectly. One thing is perfectly equivalent to the other. Because again, in total you have exactly the 132 bits on each side, whereas 4 of these 132 are reserved for checksum. The main 128 are entropy bits, just like in both cases. So again, it's a perfect expansion. In essence, it's the same. The whole point of Formosa is that now you have sentences instead of disconnected words. Why is this a good thing? Because it's easier to memorize. Okay, it has more syntactic structure. And this extra syntactic and semantic structure makes everything easier to memorize because of how human memory works. Human memory has to create associations, right? And then language gives you that, association. This is how mnemonics work. What else is interesting is if you accidentally change in your process of recollection, of mental recollection, if you change 2 words of place, for instance, you change the first with the second. Okay, suppose that when you're trying to remember, you accidentally remember dentist and nori, and instead of nori and then dentist. You will know there is an error, because first comes a nationality and then a profession, not the other way around, right? So you know there is an error. So you have more elements to detect a transcription or recollection error. You have, of course, if you change the first with the third, by itself you won't be able to notice there's something wrong. But you have more chances of detecting an error, okay? Because again, any change that you make here by itself is not enough for you to detect any error, because there is no structure. There is no semantic or no no semantic and nor any syntactic structure. But we have that there in Formosa, okay? So all in all, you have more elements to help you memorize, semantic and syntactic elements to memorize, and you have more semantic and syntactic elements to detect errors, in addition to the checksum, which again by itself is a source of error detection, right? So the Formosa is therefore more resistant to transcription errors and memorization errors, right? Is that clear now?
Yeah, that's clear now. Yeah.
Again, granted, you have more individual words to memorize. Okay, you really do, because again, you have 6 words per sentence. So time multiplied by 4 equals 24. In BIP39, you have half that, because it's 12. But because there is more semantic structure, it's more mnemonic, right? It's conceived to do that, right? What do we have here? You imagine a Norwegian dentist and a Dutch lawyer interacting with number 23, meaning, I don't know, the Norwegian dentist or the detective can choose, right? Or designer, as long as it's the E, right? You choose okay? It's either a dentist or a detective or a designer, you choose. So imagine a Norwegian, and then interacts with a Dutch lawyer or landlord or whatever, pays 23, you name it, euros for his work as a lawyer, you name it, where in a laboratory. Okay. So maybe the Dutch dentist collected a sample of a tooth from the Norwegian detective. How about that, right? A Norwegian detective maybe is investigating a case, right, in which there is a human bite So, right, so he's investigating a case in which there is a bite, and then he gives a sample to the Dutch dentist to analyze in a laboratory, okay? And the sample takes 23 days to be processed. Okay, how about that? Or pays 23 whatever euros for the dentist to analyze the biting.
Essentially, it's left to your imagination to
Correct.
decide.
The point is yes. So you use your mental imagination to fill in the gaps. The point is, the elements that you generate through Formosa are guaranteed to be strong, right? What gives you cryptographic strength? Like in one sentence, to say that in a lay person terms, what gives you cryptographic strength is the size of a haystack, right? Because how can you make an information hard to guess? If the information has been chosen randomly, and the size of the set of possibilities is large, is a large number. So imagine you're hiding a needle in a haystack. The point is, how large is the haystack? This gives you how protected your needle is. Yes, this is in a nutshell how you explain what is the source of cryptographic strength. So all in all, what you have to know and guarantee is very large is the number of possibilities. How do you know the number of possibilities? It's very simple. Here you have 64 possibilities for the very first component, and 32 for the second, and then 64 for the third, etc. So you know, and they are all independent in this team. In this team, they are all independent. So how do you know what is the total number of possibilities? You just multiply. And it's very straightforward calculation. So all in all, just like you had in BIP 39, you had 2 to the 128 possibilities. Is this large enough? Yes. Answer is very simple. Yes, it is. 2 to the 128 is considered to be a standard amount for cryptographic keys. Again, our intuitions, typically, if you are not very trained, they break. Because again, beyond a certain threshold, you are not even able to imagine anything like that. But in fact, 2 to the 128 is an astronomical number, right? It's like if you multiply the number of atoms in the galaxy by itself a few times over, you start getting close to 2 to the 128. We fail to imagine that because again, typically, in our daily lives, the few examples we have, let me just fix something very quick in just a moment. Okay. Hello. So as I was saying, the few examples we have in our daily lives of geometric growth or exponential growth, they are only locally geometric or exponential. Meaning, for instance, you have the growth of population of bacteria, right? In the beginning, or rabbits, or you name it, right? In the beginning, it is in fact geometric, but very soon, the number of individual bacterium in the bacteria you have in, I don't know, in a petri dish, hits a threshold in which it is no longer negligible compared to the amount of free space and resources available in the petri dish. So it begins exponential, but very soon it's no longer geometrical. But if hypothetically, right, you could wait 128 times the amount of time one individual bacterium takes to multiply, right? If you were hypothetically able to wait 128 as little as that, right? Because a bacterium take, I don't know, a few minutes to divide in two and reproduce by mitosis, right? Or meiosis, I don't know. Okay, if hypothetically it was possible to observe that cycle happening 128 times without the number of bacteria impacting its own rate of growth, you would in fact observe the astronomical number of bacteria. So so astronomical as there would be in fact more bacteria than the number of atoms in the universe. Of course, it is not possible because, again, within a few cycles, like 10 cycles, much less than 128, within like a few or maybe even a few tenths of cycles, like 10, 20 cycles, there are so many bacteria in the petri dish, they no longer multiply once at every cycle. They start not being able to multiply. They run out of food. They run out of like, it's not food technically, but anyway, you follow, right? They run out of space. They run out of glucose to consume, etc. So it's no longer exponential very soon. So our intuitions, they break because we tend to assume that the exponential growth is no such a big deal. Or geometrical growth is not so explosive, right, in that sense. But they really are. As long as you have, the possibilities keep growing indefinitely and keep being, in fact, exponential or geometric, it's really extrapolates our capacity to imagine, just like that. As little as 12 words give you an astronomical number of possibilities, of total possibilities. 12, like, it's a small number, right? Again, as little as 128 bits, it's just slightly more than a few hundred, right? 100 would give you, 2 to the 100 to 128 will in fact give you an astronomical number. It's so large you cannot even imagine. You cannot even think of brute forcing that. Okay, so is that clear, everybody? Hello.
Yeah.
Okay, so again, 12 words is equivalent to those sentences. What causes those elements to really be so strong? Again, the geometric aspect, that each new possibility, each new element multiplies the number of possibilities. So a small number, as few as 4 sentences, or as few as 12 words in the case of BP39, will in fact give you brute force resistance. And then again, what does that have to do with Mooncake? Mooncake is an interface to help you protect that against
such an
attack, against somebody watching you type or trying to monitor the sound of you typing. So what is happening here, right? So this is a table that breaks the connection between what is being typed to what is being meant. So if I press, let us highlight. Of course, this is just an option. You can turn it on and off accordingly, right? If I turn it on, everything I type highlights the selection. If I turn it off, it will no longer, right? So in the typical use case, it will be in fact off. But for purposes of demonstration, we can turn it on to demonstrate what is actually happening, right? So anyway, I typed A. Typing A has selected the first column. Okay. Again, what do I have to type to select, I don't know, Egypt? Or I don't know, where is Nigeria? To pay a tribute to you who is from Nigeria, right? I can reset. Okay, let us reset. Let us select Nigeria. Where is Nigeria? Nigeria is letter N. Where is Nigeria? Okay, here. Okay, so Nigeria is a semicolon, and then A, but everything is A, and then K. Now I selected Nigeria. Now this indexation is arbitrary, and it's randomized. Now the fact that I typed semicolon AK, okay, is insufficient to ascertain that I have chosen Nigeria. Meaning, if the attacker is only able to ascertain my typing, but not the indexation, he has nothing. If the attacker is able to ascertain the indexation, but not my typing, he has nothing either. He only is able to know that I have chosen Nigeria if he is able to ascertain both the indexation and the typing. Only then he's able to know that I have chosen Nigeria. Because what? Every time I reset, the indexation is shuffled. Is that clear?
Yeah.
So every time is a different indexation. If I choose Nigeria again, it will have to be what? J?
JDD.
DD. Very good. And then I choose. And then again, next menu, now it's a menu for professions, the indexation has changed it again. Again, should the user see my or somehow ascertain my typing, has nothing. Should the attacker shoulder surf and somehow capture screen, still has nothing. He only is able to get what I'm typing, what is my input, if he gets both the screen, meaning that contains the indexation, and the typing. This is harder. It's of course still possible, but I have raised the minimum requirement for the shoulder surfing to happen.
Yeah, but even though the attacker should know the indexation and what you're typing, I mean, next time you reset, that changes. So the indexation changes. So I still think you wouldn't be able to get the same value with the same indexation again.
No, look, if the attacker captures both, suppose the attacker captures both, so he captured the indexation and captured my typing. Of course, in the realistic case, a highlight is turned off. So he saw the indexation and he captured my keys, the keys that I typed. Of course, that in this case, he puts 2 and 2 and makes 4. He puts the 2 pieces of information and discovers that I have in fact chosen Nigeria. So that would be a defeat to me. So then the attacker defeated me. But then again, this process was made harder.
Yeah.
It was harder for the attacker to have done that than it would be to just capture one thing. So I made the attack harder. So this is a win, meaning the defense made sure that the attack was harder to conduct. Okay. So this is a win, right? I have already defeated, as a defender have defeated any attacker that is not able to do both things at the same time. An attacker that is able to do both things defeated me, but only those who were able to in fact get the 2 things, only those. Okay? Yeah, so this is the idea for Mooncake. Any other questions?
Okay. Yeah, so I think I earlier asked a question on the user experience and how, okay, you've already answered the question on how it ties to the Great Wall. And when I say the Great Wall, in terms of maybe using the T3 volt. So my question is, the Mooncake, it's going to be like, let's say, a library or a package that could be used by anyone.
Correct.
All you need to do is, yeah.
Correct.
Yeah.
So Mooncake makes perfect sense by itself. It's an independent and perfectly valid feature that any interface that needs a critical input could use. So any password manager, any wallet that wants to protect against shoulder surfing or against acoustic emanations of the keyboard could use it, no problem. It's agnostic, right? My features, the features that I invent tends to have this characteristic, okay? They make sense in general. Again, Great Wall, the main idea is to use it for Bitcoin, but of course, again, it is agnostic. You can use it to protect whatever you want. It could be used for a master password of a password manager. Could you be used for a password of a physical vault? You can use it to encrypt the love letters to your fiancé. You can use it to encrypt controversial comments you make about Ukrainian women. This, by the way, is an inner Brazilian joke. Okay, if you are Brazilian, you understand what I'm talking about. It's a joke anyway. But yeah, you can encrypt anything you want. It doesn't need to be Bitcoin, but again, it would be Bitcoin. Yes. Yes. Is there somebody else online? Oh no, it's just a number of screens. Okay. 3 people. Who are the third person? It's just me happening twice. Okay. So me twice plus you. The guy gives 3. Okay. Okay.
Yes.
Anything else?
Okay. On Mooncake, I think that's pretty much covered. I have my questions answered. So I think on the last call we spoke about yeah, I mean Great Wall has a strong very strong encryption, but then the question that was raised, I think on the last call was how do you handle inheritance, passing the
Excellent. Yes. So again, first of all, right, the problem of inheritance is not inherent, is not specific to Great Wall. Even if we hypothetically lived in a place that had no violence, no physical violence. So the problem of coercion or range attack is hypothetically inexistent. You would still have to have inheritance because, again, people die or become incapacitated, and sometimes that happens suddenly. So you cannot predict typically you cannot predict when you are going to die. So even if the problem of physical violence, aka range attack, was hypothetically inexistent, you would still need inheritance mechanisms. Because if you die suddenly, you have to make sure that your heirs will inherit your legacy or whatever you want to leave to them. Okay, so how to conciliate and accommodate Great Wall with inheritance? Again, my best idea, that is very simple, by the way, is like every month you broadcast to each of your heirs a time-locked wallet, okay? And you have the time of the time lock be 2 months. Okay. Now, every month you empty the wallet, the current wallet, for each heir and send it to the next. Okay. Okay. So this month, like say today is May the 1st. So every first day of the month, I send a wallet to all my heirs. And then again, on June 1st, I will transfer the content of each wallet to the next. Okay. In addition to that, each wallet is time locked for 2 months. Okay. Now, what happens when I die? 1 month later, max, or 2 tops, right? Each heir will have access to the wallet because it's time locked for 2 months. Because what? I will stop doing the cycling. If I die, I will stop delaying, right? The process of emptying the wallets and sending out all the contents to the next will stop because I will no longer be alive to do that, or capacitated. I will be incapacitated to keep doing that. If I become, I lose my lucidity, right? If I stroke my head or something, right? If I lose my capacity to do that, I will then stop doing the delaying, and then within a matter of 1 to 2 months, all my heirs will be then able to solve their time locks, and therefore we will be able to gain access to the wallets that I'm forwarding to them. Okay, so this is one way you do that. That is in fact self-custodial. Okay, you could improve upon that, and you could. There are alternative ways with slightly different properties. Okay. Another example. Okay, you have a Shamir secret sharing scheme in which all your heirs together are able to unlock your wallet. or unlock your secret. Okay. So you should trust that all of them together will not collude to steal your patrimony while you're still alive and before you want them to inherit it. Okay. So assuming they are trustworthy enough that they won't do that, you can in fact trust them that they won't do that. Okay, so it's a very good arrangement as well. Because again, the moment you die, they learn the fact, they mourn your death, okay, your passing, but then they come together and get access to the whatever you left to them. Okay. And again, that does not, at all negate the fact that you had access to that during life. Okay, so it's another way to do that. Again, the requirement is that you trust that they won't collude to take away your belongings before you die. So there are many ways to do that. Okay, what else?
Yeah. And an improvement could be made on that, where, for example, the heirs, say two people, you could make the key sharing to be between 3 people, right? For example, the two needs to come together first, but then there needs to be an approval from you, for example, I don't know, but you could be able to get a notification that, these 2 persons are trying to get access to these assets, right? If you don't respond for a number of maybe determined days, right, it automatically grants them the access, right? But then you could immediately just decline or cancel or whatever. If it's a trust breach, you could if you're still alive, you could just decide to cancel it, right? So that solved the issue for them stealing the asset when you are still alive. Or yeah.
Correct. Yes, and then the critical thing is that you don't negate the premise of self-custody, right? We mentioned that in the last AMA. So somebody in the audience mentions somebody in the audience mentions the decentralized server. And then I raised my hand and said, but wait, if you add a server in the protocol, then the system is vulnerable to a judicial subpoena of the company, or it's dependent on the company being functioning. If the company disappears, you don't want that the system collapses and becomes unavailable, right? That would be catastrophic, right? That you hire a company to do that for you, and if for any reason at all the company fails or vanishes or is subpoenaed or goes bankrupt or anything, then you lose your inheritance. Of course, you don't want that. That would be unacceptable. That would go frontally against everything Bitcoin stands for. How do you prevent that? So I made that question, and then they answered that you can use the so-called decentralized servers. Anyways, there are solutions for that. Again, and in each one of those will have their pros and cons. But anyway, the point is, again, another one. You can use the on-chain locked transactions, meaning transactions that necessitate by design a certain number of blocks to be mined. And then you sign and broadcast such a transaction. And then as the maturity comes closer, you cancel those transactions. That would be the inheritance transaction, and then you cancel the current one and then sign a new one, and you keep doing that. What is the problem? Again, this is a more reliable way to impose the time and to make sure the transaction will be there. Okay, but also you have to compromise the fact that now that the inheritance transaction is made public. on the blockchain. So people watching you and watching those transactions will of course understand it is in fact an inheritance process going on. So you now have the so-called on-chain footprint. Again, each solution that I have proposed, right? Shamir, on-chain, keep emptying and then re-transferring Lightning Network wallets, and also the other one with the decentralized server. Each one will have their own pros and cons. So, right, it all boils down to you making an educated decision on which one to use based on your necessities. Yes, but the fact is this: solutions for the inheritance problems exist. So you don't have to object. The objection about inheritance is completely taken care of. It's solved. And by the way, inheritance is not a problem that is inherent, no pun intended, is not specific to Great Wall. Anybody has to mind inheritance, not only if you are using Great Wall. Inheritance would be necessary even if there was, no problem about coercion. It would be true that you need inheritance even if the hypothetical was no violence in the world. Yes.
Yeah.
Anything else?
No, pretty much all good.
Okay, if you have more questions, feel free to ask. We had a little attendance today, but it's no problem, it's like that. We keep, of course, dialogue with the potential investors, and the current leads keep going. And yes, maybe next time we'll have more things to say and even more news about those negotiations, right? Anyway, Bitcoin keep recovering meanwhile, right? We can celebrate Bitcoin keep recovering. It's a high, all-time high. Again, we always have mixed feelings about it, right? Because again, hopefully I can close a very good deal soon, and then also surf this rising price, right, as soon as possible. Anyway, so yeah, that would be it for today, for this session. Thank you, Ibrahim, for showing up and for your questions, and we see each other next time. Goodbye.
All right, thank you so much. Have a nice one.
You too. See you.